Good morning, all. We'll begin the class in 1 or 2 minutes. Okay, we will, as usual, begin with a small recap of all the things we've learned over the last week. Lecture 16 and 17, we learned about signal conditioning and a very important topic of operational amplifiers. Most of the questions in today's problem solving session will mainly be on the operational amplifiers. Starts the slides with talk about necessity and certain types of conditioning for certain types of conditioning for, like, for example, the voltage protection, and then we move on to ideal operational amplifiers. There are several ways you can use operational amplifiers, and I've listed some of them here. We will go through each of these topics slowly and steadily and see how we can solve questions on these. Finally, Sir concluded the lecture 17 with filters. Lectures 18 and 19 was essentially about how to convert between analog and digital signals. We first Good day. So I hope I'm audible. Am I not audible? Oh no. Oh, okay. Good. Okay. So in lectures 18 and 19, we'll talk about analog to digital conversion and vice versa. We will only touch a little bit about binary digits, but it's a very important concept to know, and we'll talk about that. And the concept of resolution and sampling are fairly intuitive, but and we'll end with the Fourier series as well. Lecture 20 is about artificial intelligence, and there's, from a point of view of real life, of point of view of reality, it's a very important topic, and you should go through it. However, there are not many questions you can solve on it, so I will hardly touch that. So we'll first begin with the first question on operational amplifiers. So the first question is to find the current through the resistor R3. I will give you 2 minutes to solve this. Okay. While there are a lot of theory and concept behind the operation of the operational amplifier, the essence is the voltage at the minus and the plus of the operational amplifier will always be the same. So here the plus is grounded. Let's That means the potential at this point will be zero. I'll use a different color. Since the potential at this point is zero, we know that the voltage across the current through this resistor will, let's call that I1. I1 from the famous equation we have V is equal to IR. That means the current through resistor 1 will be V. Okay, I'll change this to V input. Will be V input divided by R1. Another important thing about operational amplifiers are that there is current cannot enter through either of these inputs. Therefore, the entirety of the current in entirety of the current R1 in this junction will move upwards into the resistor R2. Since this is at potential 0, we can say that the potential here, we know that the potential difference is equal to I into R. The current is I1 and the resistance is R2. So we have the potential difference. The potential difference, let's call this V out. So the potential difference across R2 will be 0 minus V0. Because since current is flowing from this side to this side, naturally that means that the 0 has a higher voltage than the V0. So this is the potential difference, and this is equal to I1 into R2. This means that V0 is equal to negative of I1 into R2, and we know that I1 is equal to V1 by VI by R1. Therefore, we get now the operational amplifier is an active element. That means there can be a current from this output. Because there's a current from this output, we cannot say the current through R3 will just be I1. The current through R3 will depend on what the V0 is and the resistance of R3. Therefore, the current through R3 is V0 by R3, because the potential difference across R3 is V0 on the top and it's ground on the bottom. And this can be we can solve for it using this. I hope that made sense. Okay. Now, one thing you'll notice is the potential here is inverted, and because the potential here is inverted, this is called the inverted amplifier. This is called the inverted amplifier. We can have a way in which the potential is not inverted, and that's using the non-inverted amplifier. And the steps to analyze this are almost exactly the same as we did before. So I'll give you 1 or 2 minutes to solve for this. Okay, so if you have to analyze this, the steps are, as I said, the same. Let's say that the current through R1 is I1 again, but this time one end of R1 is grounded, the other end of R1 is connected to the end of the operational amplifier. We know that the potential at both input junctions will be the same. Therefore, the potential here is also V. Since the potential there is V, when you write the we'll call this Vi again, just so that we don't get confused. So that means when you write the voltage law, when you write the equation for current here, we'll get Vi is equal to if you we'll write it like this: V0 minus Vi is equal to I1 into R1. Therefore, this becomes I1 is equal to minus Vi by R1. Similarly, when you write the equation about R2, we'll get since current is flowing in this direction, and now when you substitute back the values, we'll get Vi into 1 plus R2 by R1. So this will be the potential at the end here. As I said before, the operational amplifier is an active element, and therefore it's able to keep this potential at the end. Therefore, we do not this current I1 need not be the current through R3. Therefore, the current through R3 will just be V output divided by R3, which in this case will be Vi by R3 into 1 plus R2 by R1. Note that the one thing you will realize is that the inverting and non-inverting amplifier has a different kind of gain. Here there's 1 plus R2 by R1, and here the gain is R2 by R1. I hope this is clear. And that is how you solve these kind of questions. Now we'll be seeing the operational amplifiers in terms of using capacitors and the like. I'll wait for some time for you to solve this, and then I'll move on. Okay, So for this question, the easy way to solve this will be to recognize different parts of the circuit. The first part of the circuit is the integrator, and the second part of the circuit is a differentiator. And therefore, in the end, what you will get is V out is a constant multiplied by Vn. But we have time, and therefore we'll slowly go about each of the other parts. So, if you consider just the integrator section, wow, I have made a mistake. I'll just fix it. Okay. Okay. Fortunately, I do remember how it's run. Okay. So, if you look at just the integrator circuit, it will look like this. So, as before, we know that since this is grounded, we have the potential here as 0. Since the potential there is 0, the current here I1 will be I1 is equal to Vi by R1. Let's call this V01 because this is the first, we can consider this as the first output. We know the potential across a capacitor is V is equal to CQ, where C is the capacitance, but Q is the charge on the capacitor. The relationship between Q and I, in this case, the relationship between Q and I1 is Q dQ by dt is equal to I1, because the current comes and deposits charge on the capacitor. Therefore, we have dV by dt is equal to C into, on differentiating V is equal to CQ, we get dV by dt is equal to CI1. Therefore, that means if you integrate both sides of the equations, we get the potential difference across the capacitor, which is V01 minus 0, is equal to C into integral of I1, and we know I1 is Vi by R1. I hope that part made sense. This is why we are calling this as the integrator, because essentially, no matter, depending on the sign of the input, we can the output of this gives us a integral of the input. Now the other part of the equation was so this is the other part of the equation. I wish it hadn't been broken like this. Not even able to erase it. Okay. So similarly as before, let's say the current here is okay. This time let's say the current here is I2 because this is the second part of the equation. The steps are once again the same. We know that this V input it will be V01, and we know V01 is actually C by R into integral of Vi dt. But we'll just call it V01 here for convenience. Since current is flowing in this direction, we know that, and we know the potential across the we know the potential across the capacitor is V01 minus 0, and that will be equal to C into Q, because this is the equation for the capacitor. We know the relationship between Q and V0. Sorry, we know the relationship between Q and I2 is dQ by dt is equal to I2. Therefore, we have to differentiate this equation to get a more reasonable expression. So we get d by dt of V0 is equal to C into I2. But d by dt of V0 is, since V01 is found to be integral of V dt, we can write this as C by R into V in, because remember we had affixed this part of the operational amplifier at the end of the previous one. And this is C1 R1 is equal to C2 I2. Therefore, we know that no current will go into the operational amplifier, so all the current here will pass this way, and that gives us the normal equation again. 0 minus V02 is equal to I2 into R2, and we found out what I2 is, and we get I2 is therefore this is a very, very fancy amplifier, where the output is R2 by R1 into C1 by C2 of the input. Essentially, with this question, I wanted to show how the equations for the integrator and differentiator works. Notice that this one differentiated the input. Note that this section of the this section of the circuit had differentiated the input, and this section of the operational amplifier had integrated over the input. And naturally, if you as I said before, in the end, if you place these adjacent to each other, it will essentially cancel each other, and therefore it will just look like a gain. Now let's solve another question. Let's try. I'll give you 5 minutes to solve this question. If there are any queries regarding how this question is, If any parts of this question, please do ask. But I believe every information is there in this question for you to solve. I can. Oh, the box just says that this is a thermocouple. I'll just zoom in. If you want a small recollection, a thermocouple is a sensor which can measure temperature differences. The thermocouple has two ends, the hot end and cold end, and provided you put the hot end in one place and the cold end in the other, the thermocouple will generate a potential difference will generate a potential difference, and this potential difference will depend on the type of the thermocouple. I am saying that this thermocouple gives an output of 6 microvolt for every degree Celsius of difference between input and output. So that's the thermocouple, and you can solve this. I hope that made sense. Does the diagram? Is there any part of the diagram you need more explanation? I hope the question is fine. Don't worry, it'll take a little bit of time. Essentially, the main thing you need to remember, if you want to solve this without knowing about thermocouples, all you need to know is that the H and L, we have a different potential across these 2 points. So we can say that there's a potential here of VH and a potential here of VC. Okay, so for solving the first part of this question, I will ignore the thermocouple part and we'll come to that later. I'll first include this as VH and VC. So if you remember a few classes ago, we talked about a potential divider, and if you look carefully, this segment Oh my god. This segment is a potential divider. So if you recall those concept, you can directly say that the potential at this junction, we'll call this junction V VC. Oh, okay, not VC, VO. No, VA. If you remember the concepts about potential dividers, you can immediately say that VA is equal to VC into R2 by R1 plus R2. We can derive this also if you want. So if you consider this segment, let's assume that a current of IC is flowing here. Since no current can enter the operational amplifier through the input, the current in this branch is also IC. Therefore, we have IC into R2 plus R1 is equal to VC, because this is ground and this is VC, and I have written the directions wrong. Yeah. So naturally VC is greater than 0. So therefore the current will flow from VC down, and we know that yeah. So with this we can solve for VC. So we can solve for IC. IC is therefore VC by R2 plus R1. Since this is grounded and that's VA, we can write the equation just for the resistor R2, and we'll get VA minus 0 is equal to IC into R2. Therefore, we get VA is equal to R2 into V2 by R2 plus R1. That means since VA is this specific potential, we'll for simplicity we'll just call it VA. This junction will also be at a VA. Since that junction is at yes. Hari.
It's not visible because of yeah.
Oh, should I expand this part again? I thought we are.
Okay, thanks.
Okay, so we just said that we have found VA. Even though we have found VA in terms of all these terms, I'm not going to be writing what it's easier to just keep it as VA for the time being. So we know that by the principles of operational amplifiers, we know that this junction will also have the same potential. Therefore, this junction is also at VA. Since that junction is at VA, and we know this part's at VH, we can find the current here. We'll call this current IH. So we have VH minus VA is equal to IH into R1. This current because no current will pass through into the operational amplifier, this current IH in this junction will leave into this branch, and therefore the current through R2 is also IH. We have, so when you write the equations for R2, we'll get VA minus V out is equal to IH into R2. I hope these two equations made sense. Now, we will divide both sides. We'll with a little bit of rearranging, we'll get VH minus VA by R1 is equal to IH, and this is also equal to VA minus V out by R2. Essentially, I'm solving for IH from both sides. So, since we don't need to know what IH is, we can just solve for V out from this now. So, I will write this in a new page. So, the equation we finally found is VH minus VA by R is equal to VA minus V out by and it's R1 here and R2 here. We also know that VA is equal to R2 V so with a little bit of cross multiplication we get VH into R2 minus VA into R2 is equal to VA into R1 minus V out into R1. We want to write V out in terms of VH and VC, so we'll take this to this side and everything to the other side. So we have V out into R1 is equal to VA into R1 plus R2 minus VH into R2. Now we can substitute for VA. That gives us V out into R1 is equal to the denominator of VA is the same as the thing we are multiplying here. Therefore, this simplifies to VC into R2 minus VH into R2. Therefore, we have V out is equal to R2 by R1 of VC minus VH. Therefore, this essentially this operational amplifier is this form of operational amplifier is called a difference amplifier. As you see, it has two inputs VC and VH, and by choosing corresponding values of R2 and R1, the output is amplified by R2 and R1. Sorry, the output is an amplified version of the difference. In this question, we found that we are told that V out is equal to 5, R2 is equal to 1 mega ohm, R1 is equal to 6 ohm, and therefore we can find VC minus VH. That gives us that VC minus VH is 5 into 6 divided by 1 mega ohm. 5 into 6 into 10 power 6. Using the principles of thermocouples, we know temperature difference delta T is equal to delta V into the constant, and the constant in this case, K into delta T is equal to delta V. and we are trying to find the temperature difference. Therefore, we can write delta T is equal to delta V by K, and therefore we find that note that this is in volt and K is given in microvolt. So when you convert this to microvolt, we'll get 5 into 6 by 10 power 6. This is the value in volt. You multiply this by 10 power 6 to this is the value in microvolt, and we are dividing by 6. We are dividing by 6 microvolt per this thing. That gives us the temperature difference is the 10 power 6 cancels, the 6 and 6 cancels. The temperature difference is 5 degrees Celsius. I think I went quickly over the last few parts. Is there any do you want me to repeat any of this part? Okay. Do I have to repeat the first? Does the part that this entire thing is a difference amplifier make sense? Okay. So we found that this is a difference amplifier. I'll just write the next thing in the next page. A thermocouple is a sensor that gives us a potential difference if the two junctions of the if the two junctions of the thermocouple have a temperature difference. So this Vc minus Vh is the potential difference across the thermocouple. We can call this delta V because that's the output of the thermocouple. The thermocouple gives us a temperature potential difference given a temperature difference. The question is to find this temperature difference. We do not know what the potential difference is across the thermocouple yet, but we do know what V out is. V out is given to be 5 volt. Okay, instead of solving it like that, we can since okay, technically speaking, delta V is okay. Never mind. We'll ignore that section. Okay. The equation between delta V and delta T is delta V is equal to K into delta T. This K is what's given in the first thing as 6 microvolt per degree Celsius. Give me a second. Okay. Therefore, we can substitute this back into this equation. So we have V out is equal to R2 by R1 into K into delta T. But the units of K are microvolt per degree Celsius. So instead of writing V out in volts, we'll write V out in microvolts. We are told that V out is 5 volt. Since V out is 5 volt, that means V out is 5 into 10 power 6 microvolt. we have R2 as 10 power 6. R2 is given as 1 mega ohm. 1 mega ohm is 10 power 6 ohms. R1 is given as 6 ohm. K is given as 6 again, and delta T is what you must find. There are, oh no. Therefore, we can now solve for delta T. The 6 and 6 cancels, 10 power 6 also cancels, so therefore we have delta T is equal to 5 degrees Celsius. The main trick of this question was that the output of thermocouples are always are very small in magnitudes. In this case, it's in microvolts, and therefore, whenever we have thermocouples, we always have an amplifier at the end of it, so that the potential is a more reasonable value. The potential output is a more reasonable value. So if I had to go through this question again, the first part of the question was how I explained that this circuit is a difference amplifier. That is, given two potentials, the output of the circuit is a constant multiplied by the difference of these two potentials. Then I explained how a thermocouple is a sensor that gives us a potential difference given a temperature difference. The question is to find the temperature difference of the thermocouple. This is what we need for mechatronic systems. We do not particularly care. This is how we are reading a signal from real life and then using it in a microcontroller or whatever. So in the end, we wrote the equations and solved for the temperature difference. I hope that this makes sense. Yeah, I think the next part is about binary digits. But before we go about that, okay, you're welcome. Okay, last week we talked a little bit about 4-bar linkages and Grashov's mechanism. Oh, okay. Yeah, so in the previous animation, I was not able to show the double rocker condition. Sorry, the double crank condition. Here, okay, I'll misphrase again. You can see that this is a 4-bar linkage. Given any set of L1, L2, L3 and L4, there are always two 4-bar linkages we can form. We can call this the elbow up and elbow down configuration. So if I had changed the length A1, okay, I right now changed the length A1 to a length large enough that the Grashov's criteria is violated, and therefore you do not have a continuous flow. This would instead be a wait. Give me a second. I'll just change. Can't believe it. Okay. So I'm changing it so that now the Grashov's criteria is violated. But in this case, what would actually happen is this will be a double rocker, in the sense it will start here notice the green and the black links. The green will start here, go to this side, and go the other side. Ah, and both of these will continue rocking this way. Yeah. So this is a double rocker configuration because you can see that both links are rocking around. If I make this to 0.5, the G1 is equal to G2, and that gives us the double crank configuration. That is, both the green and the black are doing pure rotations. Both the green one is going a full 360 degrees rotation, and the black one is also kind of going a full 360 degree rotation. So in a real life system, this is what happens. But when I just write the equation, the if I just write the equation, we get that the second thing is also rocking, but in real life it would properly go as a double rocker. In this case, it's changing between the two configuration. If I make A1 smaller, notice the so, okay. Ah, okay. So here we have a crank rocker mechanism. So the green is once again have doing a full 360 degree rotation, and therefore, I mean, anytime we have the link doing a 360 degree rotation, we are calling it a crank because you're able to because many of our actuators are rotary actuators, and they are able to provide energy to the system through a rotational mechanism. Therefore, the green section is called the crank, and it's going 360 degree going under 360 degree rotations. The black line in this case does not do a 360 degree rotation. Instead, it just rocks around, and therefore this is called the crank rocker mechanism. And I think I showed you all the three kinds. We have the double rocker. We have the double rocker, in which both black and green is undergoing 360 degree rotations. And if you break the Grashov's criteria, you will notice that it will only be able to both of the green and the black will only be able to rock for certain values. So that is the concept I wanted to show about Grashov's criterion in the last class. I think that was the only question which was there in the last class. If there are any further questions about last class, please do. Yes?
Yes, sir. This question only we discussed. This only discussed. It was now very clear.
Okay.
Here.
Okay.
Thank you. Thank you.
Yeah, sure. Then, yeah, I think that's last thing about last class. There were a few questions this week about the. I have to take the question out again. Give me a second. I believe it was in the week 5 assignment. Oh no. Yeah, so in the question 8, You had found the full. Oh, I can just.
Yes, sir.
In this in this question, a lot of people had the issue that they were marked incorrectly because they had used more decimal places. And frankly, I believe all of you are right. You all of you deserve to get marks for this. Like the other TS will clarify in a few days time. I can justify why the answer here given is 0.023, and that is because the input is given as 6.0 volt. Therefore, we have two significant digits in the input. If you have two significant digits in the input, we should write our answers in two significant digits as well. And that's why the output is written as 0.023, because 0.023 has two significant digits as well. I
Yes, sir.
Yeah.
Just uh, this is my suggestion. Like in NPTEL exam also,
No, the
when we are
NPTEL exam won't have this issue. Like this is
yeah,
because
yeah,
yeah.
that's why I'm giving the feedback for
Okay,
that
okay.
one. Even then, they are mentioning there. Please mention that minimum 2 digit, 3 digit, especially for that. So the hint they will give that two digit or 3 digit. So
Yeah. Mm.
if we give here, right, this kind of the controversy will not come in future.
Yeah, I
I think
agree. So, yeah, but I do not think the same issue will happen for the final exam. So I don't think you have to worry about that. I I will. I have contacted the my higher ups, and they said that the other TAs will look into it and are looking into it. Yeah. So
whether we can get that mark revised mark for this one. Just
I cannot promise when you will get the marks, but I can say that they will revise the marks.
okay.
I'm sorry about
Thank
that. Yeah. It's crashed again. Okay. So now, we'll go do a little. We have kind of seen through the how the principles of operational amplifiers work and different kinds of methods of operational. Yeah. So I now we'll move on to a little bit about lectures 18 and 19, where we talked about binary digits. So we'll first solve a few questions on just converting the numbers from binary to decimal and decimal to binary. So yes, Hari. Yes, Hari Chandran.
yeah, I hear this OPM. This is a comparator. I got some doubt.
Where in
This
op amps.
OPM.
Okay, okay. We'll
Uh,
okay. Yeah, we'll do
discuss
that
on the
now.
last
Which question? Give me a second.
yeah,
You have a question on operational amplifiers, op amps.
yeah, which we are going to use as a comparator.
Okay. So, do you want a question on it, or do you have a specific question?
I have the doubt on
Okay,
that.
okay. Please ask. Yeah.
Yeah, when we are using this a comparator, and there is a comparator as when you use that one out, it will give that minus voltage, and another it will give us a plus voltage.
Yes.
If
Yeah.
we we use the closed loop system.
We can't. Okay. So, whenever you're using the comparator as an operational amplifier as a comparator, then we don't have a closed loop. We are only using it without a feedback.
Yeah, so it can be two output. It will come, no?
Two output.
Only one out.
There's only one output here. This is the only output to the operational amplifier.
Okay, comparator.
Yeah, this is the operational amplifier working as a comparator. Essentially,
Comparator.
if you give two inputs, V1 and V2, the output here will depend on the. Firstly, this is a this this is a simplified diagram of the operational amplifier. There are more ports, as you see in the lecture slides. There are more
Yeah.
ports in an amplifier. Is it the first one? Like here, they show there's one extra port here, but there was a much better diagram which properly showed how frightening the operational amplifier is. I think it's in the next slide, next lecture. Oh, oh, I'm sorry, it was in my materials. Okay, I'll upload a small picture with the inner workings of an operational amplifier. And essentially, there are more
Uh,
ports than just the. Yeah, this
yes,
one.
sir.
Yeah. So if you look, there are we have we have the non-inverting input, we have the inverting output, we have offsets, we have two offsets, we have Vs plus, Vs minus, and output. There are like six. There are technically like one, two. There are essentially like six inputs to an operational amplifier, and we usually just condense it to. Sorry, we are usually seven on inputs to operational amplifier, and for simple questions we condense it to three to be the inverting input, the non-inverting input, and the output. And for comparators, we also include the V plus and V minus, Vs plus and Vs minus, because those are the values for. So if V1 is greater than V2, if V1 is greater than V2, the output will shift towards V plus, and if V1 is less than, if V1 is less than V2, the output will go to V minus. So
Is of course. Then suppose sometime V in and V out is both are same, then 0 volt will be
yeah,
there. No.
yeah,
So here my question is, like minus and the plus voltage, V1 alternately we can get that. That means that graph we can get the saturation point in minus 10 volt as well as plus 10 volt.
yeah. So it'll be something like.
Yes. My, oh, alternate saturation point we can get.
Yeah.
Yes, exactly. So here the question is whether my there is a two output was discussed giving continuous when we are using the comparator.
Wait, what? Two outputs?
The two output means in periodically it may be first when we are frequently the time period measure 5 minutes or some every few seconds. If we are measuring minus 10 volt, after that plus 10 volt, if it is like it was coming, we can achieve this way. Is it correct?
Could you repeat that part again? I didn't get it. I'm sorry. Yeah.
Yeah, when the when some intermediate time we are measuring that output.
Yeah.
So when the first time if it is in the minus 10 volt, then after it
After some time
after
it
some
can
more time
change, yes.
change. So my question is here, the comparator it was giving the two output, whether we can say as a two output or one
No,
output
it
at a
only
time.
gives one output at a time, right? It does not give two outputs,
Yeah.
it gives one output at a time. And that output can change with time.
Yeah.
It's something like the output of a what's that thing called? Synchronous generator. The sinusoidal. If you take the sinusoidal voltage source, it only gives one output at a time. But the output is a range changes with respect to time. So
Yeah.
just like that,
There is a,
and,
yeah, there
and
is a doubt that question was like that.
oh, you're talking about the assignment question, whether the number of out.
Assignment question, I'm comparing with this portion. So the particularly I was compared with the taken that. So whether it was giving the two minus 10 voltage and plus 10 voltage, there is a confusion from my answer. So
Okay,
that's now
okay,
I clear.
okay, fine. It's the number of outputs is just one technically, yeah,
One
yeah, because
because
it's
everywhere I that comparator is here compare the two like greater than less than like that, but there is not like you said no, like clearly it was not output is one or two like this. Now it was okay.
okay. So that's the about comparator. I didn't include any questions on comparator because I felt that's a very simple. There's not many mathematical questions you can do about comparator. Okay. So now we'll move on to binary to decimal conversion. So we'll do you have any recommendations for the last number to check the binary expansion of? Like I'll give you 2 or 5 minutes to solve this, and do you have any numbers you want to trouble me to get a binary expansion of? I can show it. Yeah.
For 63 in 8 less of the 8 digit all are ones 63
Yeah, that's true.
all ones will come in 8 digit, that is 63, and 64 is first leftmost is a 1 all are 0.
Yeah, though that's correct. Okay. So do you? I will show how to get these. So we usually convert between decimal to binary using the short division notation. So say I have the number 63. Then I divide by 2, and when we divide by 2 we get 32. Sorry, we get 31 and remainder 1. Again you divide. You get 15 remainder 1. Again you divide. You get 7 remainder 1. Again you divide. You get 3 remainder 1. Again you divide. You get 1 remainder 1. And because we have got 1 and this is less than 2, that means we have found the expansion. So when you're writing it out, we'll first start with this and then write all these numbers. So we get 1 1, we get 6 ones. So 63 base 10 is equal to 1 base 2. Similarly, you can do it for 64, but and so we'll get 1 followed by we'll get 1 followed by 6 zeros, and that's what we had written earlier. So is there any other number you want me to find the binary expansion? Sorry, binary version? Like just go ham and give some weird number. Preferably less than 3 digits. Okay, I'll just do it for 100. Why not? So another way you can do it is, we know 100 is 4 into 25. So instead of doing for 100 directly, I'll do it 25. And when you do it 25, we get 12 remainder 1, 2, that's 6 remainder 0, 2, that's 3 remainder 0, 1 remainder 1. So that means 25 in base 2 is 11001, and 100 is 4 into 25. 4 in base 2 is 100. Sorry, 100. Therefore, 100 in base 10 will be 11001 multiplied by 100 in base 2, and that's just 1100100. Multiplication is essentially the same in whatever bases. So that is how you calculate for but finding decimal from binary has a different procedure. You can't divide in this case because so we start off by writing the place value, what we learned all the way back in second standard. So we know like if you take in decimals, we know that 173 is 1 into 10 to the power 2 plus 7 into 10 power 1 plus 3 into 10 power 0. So in the same vein, we have 1101101 base 2 is 1 into 10 to the power 1 into 2 to the power 6 plus 1 into 2 to the power 5 plus 0 into 2 to the power 4 plus 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0. I hope this correlation made sense. So now you just put it into a calculator and check. So this will be 64 plus 32 plus 8 plus 4 plus 1, which simplifies to 109, I think. Likewise, you can do it for the other question. But the steps are the same, so okay, I'll still work it out. 1, 2, 3, 0, 1, 2, 3, 4, 5, 6.
Sir,
Yes?
I have the suggestion for this one, the simple method, easy to identify that.
Yes?
Where the number will be right now, this 1001001.
Yeah.
In above that, from first digit from right onwards, in top you write that 0, 2, 4, 8 and 16, 32, 64. Wherever ones is there you need to just count it and
that also works. That's an easy way to do it. Yeah. So essentially it's suggesting that we have the number. Instead of writing it like this, I'll just write it with more space. So this will be 1, 2, 4. I'll write use a different pen. 1, 2, 4, 8, 16, 32, 64. So you just take it.
Just
So just add these numbers. So that will be 16 plus 8 plus 2 plus 1, which is 75.
yeah.
Right? I hope this is what you meant, right?
Yes.
Okay, okay. So yeah, that's an easy way to solve these questions. Note that these binary digits can be as long as you want. In a few classes time, you'll see hexadecimal numbers also, but we'll cross that bridge when we get there. So like for example, we can have 100, 100, 100, 100, 1001, and find the expansion of this. This unfortunately not a much easy way to do it. You have to work it out yourself, or better just use a calculator. Then the last part, which I had written my questions and notes on, was about the digital to analog converter using the operational amplifier. So this is the example which sir had given in the textbook. Now we can technically think of another kind of digital to analog converter which uses in the notes we have the operational amplifier used as in the notes we have the operational amplifier used as a adder, that is given different inputs you can add the voltage, yeah, the adder circuit. So technically speaking, we can also use the adder circuit to make the operational amplifier, make the digital to analog converter. In the sense, we have an input V0. Yeah. Let's say this is 1 ohm. V0. 2 ohm. V0. 4 ohm. V0. 8 ohm. And then there are switches. So depending on so this will represent 1001, and essentially this will add the voltages, and if the output here is 1, we'll get a this will also work as a this will also work as a digital to analog converter. The only issue is if you're having many more, what's that thing called, many more digits. Say you're having a 10-digit number, sorry, a 10-digit binary number, then you need resistance from 1 to 1024, and that is slightly 2512, which is slightly inconvenient, because if any of these resistors are also slightly different, it will give a small error which should accumulate. Therefore, this is one way you can make a digital to analog converter using the adder principle of operational amplifier. But as I said, the main issue here is we need a wide range of resistors. Instead, the one which is most commonly used is this method, in which we only need two sets of resistors. We only need one set of resistors of value R and another set of resistors with value 2R. We can solve for the different, like this one would correspond to 1011. So here you can look at the switches, and this is closed, this is open, this is closed, and this is open, and therefore we have 1 0 1 1, and we can show that the output here is will be 7 by 8, sorry, 1 0 1 1, that is 11 11 by 16 of the output. So do you want to work, if you want me to work it out, we can, but otherwise I rather solve other questions. And does this, I think sir properly explained how this mathematically works out also. Yes, is there?
This this switching circuit like that it was showing, no,
Yeah,
that
essentially
how
these are switches.
switches,
Yeah.
that switching circuit how we can execute in this here,
So
how it will
we can make switches using the concept of relays and
uh,
relays. A relay, one very simple example of a relay would be just a solenoid. Sorry, an electromagnet. So you have, I think it's this is there in the slides. Give me a second. It's there in week 3. Oh, it's in the. Don't remember which. Okay, it's not. It's not. It's there in one of the slides. I don't remember which one. Maybe it's position and proximity. Yeah. So we talk about switches, but there is supposed to be a part where he talks about electrical switches.
actually we are discussed in that mechanical switches like double pole double through, but
Yeah.
here like other switches, reed switches, thermal conductivity switches, uh, uh,
Okay, so essentially, no, we can generate a very simple kind of switch called a relay. Like essentially, you have it has three inputs. I mean, three junctions. Here there will be an electromagnet. Okay, this, and then here we'll have a small piece of iron which is not connected to this. So when you provide current or voltage here, the electromagnet switches on,
yeah,
and therefore the switch closes. And
discuss the NONC. Earlier it was there somewhere,
oh,
NONC contact.
yeah, it's essentially like that. So here, essentially, because of the presence of this electromagnet, all we need is an input. So we are electrically actuating this. So we can switch these switches on using relays. So you will have a bunch of relays connected to these, and depending on what the input of those relays are, the output of this, we can generate the analog output. But even though it's an
I
analog output, the analog output will still be like in steps, and that might not be what we need, but that's all we can. That's what will happen if you are going to use digital to analog. Yeah.
because I know that the relay switching circuit is very complicated. Is number of switches is more. So any other in option is there in like IC chip semiconductor
Oh,
devices.
there are definitely IC versions of this, but I don't know the specific name. Like just like we have op-amp 6009. We I don't know the specific name of the IC chip which can do this, but they're definitely IC versions. I mean, essentially, a normal transistor itself can act like a switch.
Yes. Okay.
Yeah.
Okay.
So that kind of concludes everything we have done in over the last week. If necessary, I can solve a few questions on the Fourier series, but I'm not too fond of that. we have we talked about digital to analog converter just now. Analog to digital converters are also nice simple things, but that's all theory, and there's very few questions you can have. In the in the in the AI lesson, there was a part about fuzzy logic and how about fuzzification and defuzzification, but that was a fleeting thought. So, is there any specific questions? Because if there aren't, I will just go through everything we have done in today's class again. Son Shankar, for the revised marks, like I am not the TA in charge of giving the marks, and therefore I have told my superiors that there is this minor issue about the marks, and they have not yet come back to me about it. But there are other TAs who will change the marks, and I have talked to them. I have messaged them. I do not know when they'll reply, unfortunately.
Okay, thank you, sir. Thank you so much.
No
Thank you.
problem. Yeah. Like if I was the one in charge of the marks, I would have tried to do
You have
something
done
by
it.
now,
Yes,
but I can't do it.
yes,
I'm
yes.
sorry. Yeah.
You can understand. Yeah.
Yeah. So, is there any specific questions about last week's lectures? Like in one of the doubts the student had asked in the forum, he had asked which I don't have the thing. Essentially, the question was something of the form. Give me a second. Week 5. Yeah. The question was. Oh my. Yeah. He had asked why 11 is B and not A. That's because A would be 10. So we have. So when you convert decimal to binary, sorry, decimal to hexadecimal, we have So from 0 to 9 is the same. Then 10 in decimal will be A in hexadecimal, 11 in decimal will be B in hexadecimal, and so on. That is why the 11 is a B. I saw this question, but I don't know if it's clarified for him. I don't think he's in class today also. So if there are no more it's a question. Oh yeah?
Sir, I need to discuss regarding that our uh, this 8-bit DAC,
Yes.
that in our in our lecture there is option, we converted 8-bit to that 0 to 10 voltage.
Yes.
Okay. Uh, the graph we discussed in that slide, 1.25 voltage, this one. Can you open that one?
Is it
In
this?
lecture 19. Lecture 19.
Yeah, lecture 19.
Yeah. There is a slide, one graph will be there, 0 to 10 volt, divided by 8. Yeah, here, somewhere down. Somewhere down. The voltage divided by 2 to the power of 8, divided by 0 to 10 voltage divided by 8, and the voltage will come 1.25 voltage in that this one uh, voltage difference. Let me check.
Can you tell me the slide number?
Let me check, sir. I am checking.
Yeah, fine. Uh, okay.
Okay, you can get good. I will come back
Okay,
afterwards.
fine. Is there any further question? I will take a small 1 minute break because I want to change my headphones. Give me a second. I unfortunately cannot change the headphones while the recording is going on, so that's unfortunate. Okay, so if there are no more, okay, I will clarify Harish Chandran's questions when he gives a slide. So until then, we'll just go through everything we've done about op amps. So essentially, the I felt the most important thing we learned in this week was about op amps. The important thing about op amps are two things: the output of the op amp, is specifically the voltage, and because the op amp is an active element, it is able to provide current through the output. The input does not take current in, on the other hand. Therefore, and primarily the two inputs of the op amp will always be kept at the same voltage. In certain literature, it's sometimes referred to as there's a virtual voltage at the two ends of the op amp. So, for this particular question, since the plus side of the plus input of the op amp, so the non-inverting input of the op amp is grounded, that means the inverting input of the op amp has a virtual voltage of 0. And with that information, we solve the rest of the circuit. So, given the fact that the potential at this point is 0, we have the current through R1 is equal to VI by R1. Since no current enters the operational amplifier, this entire current will pass through the resistor R2, and therefore we can find the output voltage. The output voltage V0 will therefore depend on R1, R2 and VI, and we found this relationship. We found that minus VI is equal to R2 of VO is equal to minus VI into R2 into R1, R2 by R1. After that, getting the voltage current through R3, we essentially do the same relationship. V out divided by R3 will give us the input, will give us the current. Oh, by the way, I have uploaded the questions in the give me a second. So before you come to class, you can I am very sorry. I thought the PDF was uploaded. It seems it's still uploading. Oh, I am. Oh, never mind. It is uploaded. Okay. So I had uploaded the questions I had uploaded the questions. So in case you want to come to the class with preparation, you can look at the questions and solve the questions and then come. And if you do that, we will have
Yeah. Thank you, sir. It was great. I was seeing that all the video and this PDF notes are uploaded.
Yeah. Okay, so I just wanted to add that I forgot to mention this earlier in the class. Okay, so that concludes about the inverting amplifier, and then we have the same concept for the non-inverting amplifier. The gain is slightly different, but that's how the maths goes. Then we saw how the integrator and differentiator works, and note that there are plenty of other circuits. Like for example, there is the difference amplifier, and then there is the summing amplifier, which I talked about shortly for the DACs. Sorry, for the digital to analog converter. There are things called instrumentation amplifiers also, which are essentially a series of operational amplifiers, each of them amplifying the previous input. And there is even a logarithmic amplifier, because we know the current through a diode is exponential, and therefore I didn't see your question, Tanvi. Yeah, but yeah, if you go to the Yeah, if you go to the website, if you go all the way to the bottom, there's problem solving session, and when you click that, you can click here to open the Google Drive link. Like, click here. Essentially, the important part of operational amplifiers is its incredible usage and different signals related aspects. So we can add signals, subtract signals, and those things, and that's very important for signal conditioning prior the study of microcontrollers. And I've gone through everything again. I'm not sure what to do any is there any specific question? I'm sorry, I should have made more questions once again. Yeah, it's no problem. Like, technically the class has 20 more minutes, and I will be here for 20 more minutes. If there are any questions, I'll be yes, Harichandran.
Yeah, I got it. That there is a lesson 18, slide number 1624.
Okay, I'll check. Yeah. 16 Shannon sampling theorem.
1624.
Oh, wait. Lecture 18, slides 24.
1624. 16.
There's no graph.
Timing.
Oh, this one.
Yes.
Oh, okay.
Yeah. So here, if you above slide, if you go, sir, first slide and second slide, this it be preface.
Okay.
Here, uh, yeah, the question is here only. My question is here. Like code with q is equal to v minus divided by n.
Yeah.
Okay. So here it was already the output states are mentioned 0 to n minus 1.
Yes.
Correct.
Yeah.
Because 0 is here one of the input, 1 bit input. So other 7 input we need to take as some positive reading or negative reading. So that 8 bit it will calculate here.
Yeah.
Is it correct?
Yeah.
Okay.
I mean, there won't be negative. Here, there'll just be positives from 0 to that number. Yeah.
Yeah, 0 to that. But 0 is here one of the bit we need to calculate. Correct.
Yes.
So here this is a n minus 1 we need to divide, but here that in this example the 10 was divided by 8.
No.
It was the
n
giving
minus
the result
1. N minus 1 is the last number. So, for example, here for 2 to the power 3, the n minus 1 will be 7. So we can only represent things until 7. But we still have 8 divisions.
I got it. I clear that.
Okay. We have 8 divisions. And because there are 8 divisions, we must divide by 8.
Yeah, that's correct. Correct. When the output, when I'm linking with that our question also here, because here normally that your output is 10 voltage is a maximum voltage.
Yeah.
Correct. So if you are using that 8 bit, 10 divided by 2 to the power of n minus 1. So
that way,
only we need to divide.
2 to the power.
So here why we divided directly 10 divided by 8? Because it should be divided by 7 only. No, my question is here.
But we still have to represent. Wait, give me a second. Let me think about your query.
Yes, because of course, because 0 is one of the digit. Another 7 digit we need to store it. Okay, so another 7 digit, the last digit will be a 10, correct?
Give me a second.
Yeah, you can calculate.
But if you do it this way, we get.
So my question is here, it should not be 1.25, it should be 1.42, then that 8 bit will be divided into the 10 voltage.
I see your point. I had not considered this. I will clarify this and come back to you. Okay. I'll tell you next week. Yeah.
Because,
Yeah.
because when I am comparing with this one as a example, which compare with my question on that fourth one, this one, there 8 bit, if I'm directly divided by 256, that voltage, which is we are discussing now, one question number 8, no? There
Yeah.
is a number of digits,
Yeah.
0.23475. Somebody will get divided by 255, that will be a 23475. Somebody divided by 256, then it should become on the 23471. So in this example itself, there was a conflict. Here it was not used that 2n minus 1. So my question is, if you consider as a 10 voltage as a last digit 8 bit, then 1.4 bit
I
is a step voltage.
Yeah, I get your thing. I will clarify this. Like, essentially, for larger values, this is not that big of a deal, because if we have 10 to power 3, 10 power, sorry, 2 to the power 10 digits and all, it's a difference. It's a difference between dividing a 1024 and 1023, which are almost exactly the same.
Yeah,
But
but of course,
I will clarify this and come back to you next week.
but that of course, wherever we show the digital electronics, the zero is one of the first
Yeah,
digit.
you're right. You're right. Yeah.
Balance only, if you 256 code, then you need to use the only 255 is a positive voltage or something voltage we can measure. Zero will be always will be that one of the off voltage we need to record it there.
Yeah. You are you are correct. I will check. You're logically right. I'll just check this on tell you. Yeah. Yeah. I will tell you this next week. I will. Is there any other question? I'll. Yeah. There's still 10 more minutes. Oh, have you checked the video? Yes, yes, Silas. I think you'll write down the question, right? Yeah. While Silas is typing the question, have you seen the video recordings? Because I wanted to check if you never mind, never mind.
Yes, I was checked that only that video one something that audio from your side something disturbance
Yeah,
was there.
there's a double sound which I was able to hear, and that's why I
Yeah,
shifted to this earphones
yeah.
headset. But this headset is really not comfortable. I wanted to test another one, but it was not working well. Okay.
After that, after using this headset, it was very clear that audio was very clear.
Okay, okay. For basic electronics, I can share name of a textbook, but I need to think a little. Give me a second. I have it in my. Wait. So for my college, we had used the book Electrical Circuit Theory and Technology by John Bird. I'll write it out. And if I'm honest, I my professor for basic electrical was not fantastic, and therefore I studied everything I know about electrical from this book. So I feel like this book is a solid way to study. If I remember correctly, this book also has theory about operational amplifiers. Yeah, it has 10. It's a good book. No problem. Oh sure. Like my name is Naveen Rafael, and I am a PhD scholar in IIT Madras. Because I'm part of the PMRF scheme, I'm supposed to TA for NPTEL. I can TA for NPTEL courses, and therefore I'm TAing for Mechatronics because Mechatronics was one of my stronger subjects in my undergrad. And yeah, that's essentially it. I'm working on mechanical design and processes in specific. Yeah, I'm also mechanical. I'm also studying in mechanical engineering. I am expected to take 2 hours of class every week. I mean, all of us are taking mechatronics course, so I'm not surprised all of us are mechanical. So I'm supposed to take 2 hours of class every week for the entire year. After this course gets over, I'll wonder for a while what to do. But yeah, I'm just to clarify, this is my first time also teaching, so this is my essentially my fourth class. Like after this class gets over, I'll stop the recording in 3 minutes and then I'll upload it and you can see it on YouTube again. You, mm, I do not. I mean, technically speaking, I guess you can do that, but unfortunately, it depends on the PhD scholar themselves. Like, my the in charge of PMRF has explicitly told me that it's our duty to search for places to TA and teach, but we are in the end expected to teach for a specific amount of hours every week. So if there is a PhD scholar from IIT Delhi who wants to take in your government ITI, you can uh, try contacting them. But unfortunately, I don't have details about where the PMRF, which PMRF students are in IIT Delhi, and so on. No, there's no specific level. For example, people in chemical and physics sometimes teach in can teach in for schools also. But we just have to teach. We just essentially have to share information. So it doesn't matter where exactly we teach, I guess. We just have to, but it has to be related to your coursework. Essentially, I'm in mechanical, and therefore I can essentially do whatever things in mechanical and slightly a little bit of physics also. But I cannot go and take humanities courses. Okay, that will conclude today's class. I'll stop the recording, but I'll stay around for a while.